Hey everybody, how's it going? This is Caleb with DevSlopes, and in this video we're going to be talking about the heap data structure, and we're also going to learn how to build one in Swift, which is pretty neat. So first I want to just kind of review what the heap is and how it works. Basically, heaps can operate in two ways: min heap or max heap. A min heap basically prioritizes the smallest values at the very top, and a max heap does exactly the opposite. It prioritizes the largest values at the very top. Now, each heap starts with a parent node, and then it can have two children nodes, just like so. So this top one has two children. This one here is a parent. It has two children. A node can act as both a parent and a child, except for the very tippy top. So another thing to know is that the child nodes are always bigger than their parent node. So here 2 is the parent, and the children are 3 and 8. Both are bigger. Here, 3 is a parent node, and 4 and 7 are both its children nodes, which are both bigger. So that's how that works, going down. Another thing to note is that the index of heap items start at 0, just like an array, and then go top to bottom and left to right. So we start with 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. And what we need to be able to do in our heap is to be able to access the index of a parent node for a child node. We also need to be able to access the indices of both children from a parent node. And we're going to write some code to do that, but we also need to think, if I add in a new item, okay, like down here at the bottom, maybe index 21 or something, it needs to be able to tell whether or not the parent node is larger than that value. And if it is, then we're going to switch it until it fits where it's supposed to be in the heap. Now, you might be wondering, why would a heap ever be useful in real life? Well, think about this. Imagine that we are using a max heap where the largest values are prioritized and moved up to the top, and the lower values are more down towards the bottom. Now, of course, you can tell it's not perfectly organized where it's going, in numerical order, like 2, 3, 4, 7, 8. Like, it doesn't work that way. But generally speaking, the largest values are at the top, and they're prioritized that way. So obviously, a min heap gives you the minimum value at the top. A max heap gives you the maximum value at the top. So imagine that you're working in a hospital, and their intake system for new patients, maybe at the emergency room, is a max heap, because they want to prioritize the oldest people who come in first. They should receive care first. Maybe that's how it works. So let's say someone comes in, they're added into the heap, and maybe their age is, 75. And we got to think about this flipped, because this is a min heap, but basically their value would be bumped up to the top, and they would be put in priority number 1 because they are the oldest. As soon as maybe they have received care, they could be removed from the heap, and then the rest of it would bubble all the way up, and so that the next oldest person would be at the top. That's how they work, and that's how they could be useful. The same could go for maybe a pediatric clinic, where the youngest children would be prioritized first. Okay, so let's go ahead and let's pull open Xcode and let's build a heap. So get started with a new playground, and we're going to go ahead and just create a blank playground, and let's just call this Heapify Me. Cap'n. Just save it wherever you want. I put mine on my desktop. I'm going to make the window full screen here and get rid of all of that and just import Foundation, because we don't need any of the fancy UI kit stuff in the playground. For now, we just need Foundation because we're using Swift. So let's go ahead and let's create a struct, okay, called a min heap. And that's what we're going to do. We're going to create a heap that is a min heap. We could create just a heap struct and then write all the functions for min and max, and maybe use some type of enumeration to determine whether it's min or max. But for now, let's just go ahead and focus on a min heap, because a max heap is exactly the same, just opposite. So we're going to write some functions in here that are going to be private, that only the struct can access inside. And they are important. There are 3 groups of functions. The first group of functions is going to be for getting the index of a particular node. Get left child node, get right child node, and get parent node, or I should say index rather than node. And so what we're going to need to do is to first write the function that's going to get us the index of the left child. Because let's imagine that I am a parent here and I want to know what the index is of maybe child on the right. So I could do a formula and a function, pass in my index, and depending on my index, I could basically tell you where it is and what index it's at. So we're going to start by writing a function to get the left child index, and it's going to be a private function called getLeftChildIndex. We're going to pass in the parent index here, and of course that's of type int because an array uses int as its way to manage indices. And because we're getting an index back, we need to return an integer. So in order to actually get the index of the left child, we're going to return 2, okay, times the parent index plus 1. Okay, now let me show you how that works. So this is our first item, and it's at index 0. We're going to use an array, actually, to store our heap because the index format is the same. So index 0 is here, so we're going to do 2 times 0, which gets us 0, plus 1, gets us the left child node. Very, very cool. That's at index 1. Now, getting the right child is going to be basically the same, just we're going to add 2 instead of 1. So private func get right child index, like so. We're going to pass in the parent index, of type int, and we're going to return an integer because, of course, we're getting the index. So return 2 times parent index plus 2. And that works the same way. This is index 0. 2 times 0 is 0 plus 2 gets us 2. So index 2 is where the right child is. So we go 0, 1, 2. There's our right child. And it works for any of these. This is index 1, 2, or 0, 1, 2, 3, 4. So if we wanted to know the right child index, we would take 4 times 2, which is 8, and then plus 2, which is 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gets us the index of the right child. It's pretty cool. So let's go ahead and let's write the function in order to get the parent index. That's also going to be a private function, get parent index, and we need to pass in the index of a child. So child index of type int, and we're going to go ahead and return an integer. And the function for this is we're going to return child index minus 1, all right? And then that whole thing is going to be divided by 2. Let me show you how that works. So this is, well, let's see. We're getting the parent index of this, so we should get the index 2. So what we're going to do is we're going to take the index of this node, 0, 1, 2, 3, 4, 5, and what we're going to do is we're going to minus 1. So 5 minus 1 is 4, and then we divide that by 2, which is 2. So 0, 1, 2. The index is 2 for the parent node. So now we have the functions we need in order to actually interface with our heap, and that's cool and all, but let's go ahead and let's compile these together. These are functions for getting the index, and that's great. So let's go ahead and let's move on. Oh, that's weird. It looks like that curly bracket turned dark on me there for a second. Now we need to go ahead and basically write some Boolean check functions, and these are going to check whether or not an item has a left index or a right index, because in some cases it might not, right? This parent has a left child but does not have a right child, and so that would tell us that's where that item needs to go. Pretty cool. So we're going to write some functions to determine those different things. Private func has left child, okay, and we're going to just pass in an index, okay, and we're going to return a Boolean. Alrighty. And in order to do this, we're going to go ahead and say return get left child index. Alrighty. And we're going to pass in whatever index we have. So let's say, it's a parent at index 4, and we're going to get the left child of that parent index. But what we're going to say is if that index is less than the total amount of items in our heap. So let's think about this. If our heap here is, well, let's see, if this was the 20th item, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, what that means is that there are really 18 items. So if the index here is 17, and if that is less than the total number of items, right? The index is 17, the total number is 18, right? So if that is if that is less than, that means that there is a left child index, okay? So what we're going to do is we need to actually create the array that is going to hold all of our heap items. So go ahead and create an array called items, items, and it's going to be an array of type int. If only I could type. And we're going to go ahead and just initialize it as an empty array here, and we're going to say if it is less than items.count. Okay, if that's true, it'll return true. If it's false, for instance, index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we pass in the left child index of 9, okay, and we get what the child index should be, which in this case would be 19. 19 is not less than 18, so therefore it knows it does not have a left child. That's how it works. So we're going to do it again, but do it for the right child, which is actually going to be the exact same function. So for time's sake, I'm just going to copy and paste it and just change the wording. So get has right child, we're going to use the function get right child index. And if it's less than items.count, we know that we are not doing the right thing. So now we need to write the function to check if a node has a parent. Okay, so private func has parent, and we're going to pass in the child index. Well, let's just say index to be general. Has a parent. We're going to check and return a Boolean. Okay, let me make some more space so you can see what I'm doing here. And so basically what we're going to do is we are going to return get parent index. Alrighty. We're going to pass in the index, and if that index is greater than or equal to 0, right, we know that there is a parent because, so if, let's say we pass in, index 1 here. If 1 is greater than or equal to 0, it has a parent. Here, if it's greater than or equal to 0, it has a parent. So basically everything will have a parent node because this index 0 is equal to 0, and so this node is a parent, obviously, and it is its own parent, which is kind of weird to think about. But anyway, that's how it's going to work code-wise. So now what we need to do is we need to be able to return a certain item from the heap, right? So we have our array of items. We need to be able to return an item. So this is our third section of functions, and it's going to just be functions that return an item from the heap. So we're going to write 3 more private functions here, private func, and this one is going to be to return the left child, okay, at a particular index. And what it's going to do is it's going to return an int, okay? So in order to get it, we're going to return something, and it's going to come from the items array. And all we need to do is to get the left child index, get left child index, and for a particular index. So that will return the item at the index that we set, right? So let's say that we're talking about a parent node, and we want to get the left child. We can actually just call the index from the parent, and it will return the left child for that parent. So we're going to do the same thing here for right child, and I'm going to just copy and paste it for time because it's the same exact thing, right child, but we're going to use our right child function. Next, we need to be able to get the parent. So private func parent, all right, and we're going to pass in an index here of type int, and we're going to return an int. Now we're going to return items, okay, and we're going to pass in get parent index for index. So if we pass in the index of maybe a left child, this will tell us what its parent is, which is pretty cool. So now this is where we're actually going to write out the operations for our heap. And like I said, when we're dealing with a heap, if we add in a new value, say 3 here, we need to be able to check to see if this value and its parent are in a good relationship. And right now they're not, because 3 is smaller than 9, so it should be in this place. So what we're going to do is we're going to swap these two, and then we're going to check it again. So we're going to swap the index of 3 and 9, and then we're going to check, okay, 3 is still smaller than 4, so we need to swap 3 and 4. And then obviously 3 and 3 are equal, so they can be in the same place here, and that's fine. But we're going to move on. So we're going to go ahead and write the swap function, which is going to swap 2 items. And so let's go ahead and just call this heap operations. And this function is going to be private as well because it just needs to happen on an internal level. Private function swap, okay, index 1 of type int and index 2 of type int. And this is not going to return anything. We're just passing in values and mutating them. So we're going to basically save one as a placeholder, set the other one, and then set the first one back to whatever we stored in the placeholder. So let placeholder equals items at index 1. All right, so we're going to save that in that little constant there. Then we're going to say items index 2 is equal to items at index 1, like that. And then, oh wait, no, I'm doing this backwards. Index 1 is supposed to be set to the item at index 2. Alrighty. Then we're going to go ahead and set items index 2 to be equal to the placeholder. Okay, because we changed the value of index 1. We just stored it in memory there, which is pretty cool. And then all that's doing is just swapping the place, the index of two variables, or two values, I mean, in our function. Now, we are getting yelled at because it's saying that this function inside of a struct needs to be marked as mutating because it's actually mutating the way that items is lined up. So let's go ahead and add the mutating keyword there, and our little error message will go away because it can then have the permission to mutate the items array. So a heap has three functions very similar to a stack. We have peek, poll, P-O-L-L, and add. So add is like push, poll is like pop, and peek is just like peek. So we're going to write those three functions now. These ones, peek, poll, and add, are all public. They're ones that we actually want to interface with because peek allows us to look at the very top item of our node, so we could check, what patient is in that spot if we're talking about our hospital metaphor. Poll is going to remove the top item and return it, okay? And then add is going to push a new item in. So let's go ahead and write this one, public func peek, alrighty? And it's going to return an integer to us. And so if items.count is not equal to 0, alrighty, we're going to go ahead and return item at index 0, okay? Because that's the top item in our array. But if that is not the case, if items.count is equal to 0, we're going to call fatal error, okay? Because that would be a problem. There's nothing in our array. So that's how peek works. It's going to return the top item. Now we're going to go ahead and do another public function here called poll. And poll is actually going to return an integer as well, like so. But we are going to be modifying the array because we remove an item and then return it. So we need to set this to mutating. Now, what we're going to do is we're going to check again if items.count is not equal to 0. We're going to do stuff like modifying the function and removing it. Then we're going to go ahead and say else if there is 0 items, we're going to call fatal error. So here we go. What we need to do is we basically need to store the item at the first index. So let item equal items at index 0. Alrighty, we're going to just save that in its place. Then what we're going to do is we're going to go ahead and set items at index 0 to be equal to the very last item, which is the new one that we have added, or most recently. Alrighty, so we're going to call items items.count -1. So we're going to go ahead and move the last item in our heap, okay, all the way up to the front. Okay, and then what we're going to do is we're going to go ahead and call a function called heapify down. We haven't written that yet, but then basically what we're going to do is heapify down is going to basically check the indexes and say, okay, 18, that is bigger than both of these. It needs to go down. Okay, 18, still bigger than both of these. It needs to go down. 18, still bigger than both of these. It needs to go down. 18, and it's basically going to help it go all the way down to where it needs to be. This is what we're doing, is we're removing the first item, and then we're heapifying everything so that everything knows where it should be. Now, we're going to write the function heapify down in just a second, but then at the very end, after we reorganize everything, we're going to return the item that we initially saved and removed. Okay? So that's poll. That's going to remove the first item and then return it. And now we need to go ahead and create the add function. So it's going to be a mutating function, and it's going to be public. And we're going to go ahead and just say add, and it's going to be an item of type int, because that's the type that our function is. And so we're going to go ahead and do that. We're going to say items.append, add the new item, and then we're going to need to heapify up. Okay, because if we add a new item down here at the bottom, like let's say it's 3, that should be switched with this. So we're going to heapify up, goes there. We're going to heapify up again, and it'll stay there. Okay, so that's where heapify up comes into handy. So this video is getting a bit longer than I had anticipated. So we're going to go ahead and cut this one short and head over to the next video where we're going to actually write the heapify down and heapify up functions in order to rearrange our heap. And then we're going to actually create an instance of it and play around with it so you can see it visualized. Let's head over to the next video and let's keep learning about the heap.